So today we're going to be looking at bond energies or bond enthalpies and how we can calculate the enthalpy change of reactions, right, using bond energy data. We're first going to define the bond energy, okay. The bond energy is also known as the bond enthalpy, okay. So we can say bond enthalpy or bond energy is defined as the energy needed, okay, the energy needed to break 1 mole of covalent bonds, okay, 1 mole of covalent bonds in the gaseous state, right, in the gaseous state. Now obviously when we break covalent bonds in the gaseous state, we end up making gaseous atoms, okay. So when we break covalent bonds in the gaseous state, okay, we end up making gaseous atoms. Bond energies can be divided into two categories, okay. So when we talk about bond enthalpies, okay, we have two broad categories, all right. The first category that we have is, okay, some bond enthalpies that we use are exact bond enthalpies, okay, and exact bond enthalpies are for diatomic molecules, okay. For diatomic molecules we use exact bond enthalpies. So for example, right, if we look at something like nitrogen gas, right, it's a diatomic molecule. Here we have the N triple bond N, okay, and the bond energy for this is 944 kilojoules per mole, okay. Similarly, if you look at oxygen gas, again we have a diatomic molecule, okay, O double bond O, okay, the bond energy for this is 496 kilojoules per mole, okay. You don't have to remember these values, this data will be given to you, right. You have something like HCl, another diatomic molecule, right. Here you have the HCl single bond, right. The bond energy for that is 431 kilojoules per mole, right, and so on, right. So these are exact values, okay, these are exact values. Now the bond energies that we use for polyatomic molecules, okay, the bond energies that we use for polyatomic molecules are known as average bond enthalpies, okay. They're known as average bond enthalpies, okay, and they're for polyatomic molecules, okay. They're for polyatomic molecules, okay. So these are non-exact values, okay, these are going to be non-exact values. So for example, right, let's say that I have a methane molecule, okay, let's say that I have a methane molecule, and let's say I have 1 mole of methane, okay, let's say I have 1 mole of methane. Right now we have 4 CH bonds in methane, right, we have 4 CH bonds in methane, and if you want to figure out the bond enthalpy or the bond energy of the CH bond, okay, we're going to break the first bond, we're going to break the second bond, we're going to break the third bond, we're going to break the fourth bond, right. We ended up breaking how many moles of bonds? 4 moles, okay, and the energy required for each time I break the bond may be slightly different, but I've broken a total of 4 bonds, and I can take the average of the 4 bonds, and I get the CH, the average CH bond enthalpy for methane, okay. So the CH bond has a certain bond energy in a molecule of methane, right. Then let's say I have something like ethanol, right, let's say I have something like ethanol, right. Now in ethanol, right, I have an OH group, so the bond energy of the CH bond may vary slightly from that of methane. The average energy of the CH bond in something like methanol may be different from the average value in methane, okay. Similarly, if I had something like ethene, for example, right, in ethene I have C double bond C, right, and we know that here the carbon atom is sp2 hybridized, okay. So again, the CH bond may be slightly different, the bond energy of the CH bond or the strength of the CH bond may be slightly different in ethene, it'll be slightly different in methanol, for example, it'll be slightly different in methane, right. They're going to have different values. So the bond energy, the data that we get in the data booklet, okay, the data that we get is the average of the CH bonds from a given set of molecules, okay. So chemists will decide, we're going to look at 100 different molecules, we're going to figure out the average, CH bond strength for each of those molecules, and then we're going to take the average of all of those CH bonds to figure out the average CH bond strength, okay. So the value that will be given to you in the data booklet, for example, okay, for the CH bond is 410 kilojoules per mole. Okay. Now this value is the average value for all the different molecules that we chose to take the average of. It's not the exact value for this particular molecule or this particular molecule. So this value that we're getting here, for example, is, okay, we're figuring out the average CH bond energy for methane, for example, by breaking these 4 bonds and then dividing that value by 4, the energy needed for breaking 4 bonds, divide that by 4, we get the average bond energy for methane. Okay, we do the same thing with the 3 bonds of methanol. We do the same thing with the 4 CH bonds of ethene. Okay, and we're going to do that for a certain number of molecules that people have chosen, right? And we're going to get different average values for different molecules. Okay, and then we're going to take the average of all of those. We take the average value of all the CH bond energies, okay, for many different molecules, and then that's the value we report in the data. Okay, so this value doesn't apply to any specific molecule. It's not an exact value. It's just the average value of a certain number of CH bonds or a certain number of molecules that we have chosen, and determine the average bond energy of those CH bonds from those molecules. Okay, so this is a source of inaccuracy. When we're doing calculations, right, we're going to be using this value in our calculations, for example, if we add methane, okay, but the actual value may be different, the actual bond energy value may be different from the average value. The exact same thing would apply to something like the OH bond. Okay, so for example, right, we have H2O, right, we have something like, let's say, methanoic acid, right, we have something like methanoic acid, let's say, we have something like, methanol, for example, right. The bond energy, the OH bond energy is going to be different for each of these molecules. The OH bond energy is going to be different for each of these molecules, but in the data, again, these are all polyatomic molecules. Okay, in the data, the value will be reported as 460 kilojoules per mole. Okay, again, this value doesn't specifically apply to any one particular molecule. Okay, it may be different. It may be different from the actual bond energy for a given molecule. Okay, this is just the average bond energy of a certain number of molecules that we have chosen. So you have the carbon-carbon single bond, for example, right, in different organic compounds. The average value for this is 350 kilojoules per mole. So by definition, of course, the bond enthalpy or the bond energy will always be endothermic. Okay, it's always endothermic. It's always endothermic, right, because energy is needed to break bonds. Right, so always endothermic. Right, the bond energy, and as the definition states, it's the energy needed to break 1 mole of covalent bonds in the gaseous state. Okay, so there have to be gaseous covalent bonds. All right, so for example, if we were talking about, let's say, something like chlorine gas, right? If we had, let's say, 1 mole of chlorine gas, right, and we would form gaseous atoms, right? Here, what we're doing is we're breaking the Cl-Cl bond. Okay, and we have 1 mole of Cl2 molecules. Remember, each chlorine molecule has a single bond, right? So if you have 1 mole of molecule, we're breaking 1 mole of gaseous covalent bonds. Okay, and whenever we break covalent bonds in the gaseous state, we make gaseous atoms. All right, so the enthalpy change for this process, as I've shown it, is simply the chlorine-chlorine bond energy. Okay, and this is equal to positive 242. On the other hand, if I had something like this, right? If I had, let's say I had bromine liquid, okay, and from bromine liquid I was making gaseous bromine atoms, right? Now in this case, the enthalpy change of the reaction, right? The enthalpy change of this process is not the BR-BR bond energy. The reason why is because bromine is not in the gaseous state. Okay, so when we want to do this, what we're first doing is we have 1 mole of bromine. We're first vaporizing bromine to form gaseous bromine molecules. And so we're first vaporizing bromine, and then the energy needed to break those covalent bonds in the gaseous state will be the bond energy. Okay, so the enthalpy change for this process is equal to the enthalpy change of vaporization of bromine. Right, enthalpy change of vaporization is when 1 mole of bromine is vaporized, and then we're breaking 1 mole of gaseous covalent bond, so that will be the Br-Br bond energy. Okay, so the enthalpy change for this process is the enthalpy change of vaporization of bromine plus the bromine-bromine bond energy. So again, bond energy only applies when we're breaking covalent bonds in the gaseous state. All right, now let's say that I have a reaction, okay, and in this reaction I have reactants, okay, and what I'm doing is I'm making products. Okay, I'm making products. I want to find the enthalpy change of the reaction. Okay, I want to find the enthalpy change of the reaction, and here bond energy data is given to us. Okay, bond energy data is given to us. Now, if I want to find the enthalpy change of the reaction using bond energies, okay, let's draw an energy cycle to show how we can calculate the enthalpy change of the reaction. But what we can say is that when reactants convert to products, right, the first thing we do is we're going to break the bonds, okay, in the reactants. Okay, let's assume that all the reactants are in the gaseous state and the products are in the gaseous state. Okay, so in order for reactants to make products, we're going to break the covalent bonds in the reactants. Okay, we're going to break the covalent bonds in the reactants, and we're going to end up making gaseous atoms, right? So we break all the bonds in the reactants, and then new bonds form, right? And we end up making the products, right? New bonds form, and we end up making the products. So a reaction can be thought of as taking place in 2 stages, right? The bonds in the reactants break, making gaseous atoms, and then all those atoms recombine to form new products. Now what we can say is that the energy change, right, from reactants to gaseous atoms is the bond energies of the reactants, right? It's the bond energies of the reactants. And the energy change when gaseous atoms form products is the negative bond energy of the products, right? The reason it's negative is because bond energy is for when bonds break to form atoms. Here we're making bonds, right? Bond energy will always be positive. We're making bonds, that's bond formation. So that will be the negative bond energy of the products, right? When gaseous atoms combine to form bonds in the products, that will be an exothermic process. So that's going to be minus the bond energy of the products. So we can say that the enthalpy change of the reaction is equal to the bond energy of the reactants minus the bond energy of the products, right? We can say that the enthalpy change of a reaction is equal to the bond energy of the reactants minus the bond energy of the products. Okay, which is the same as saying that it is the bond energy of the bonds broken. Okay, the bond energy of the bonds broken minus the bond energy of the bonds formed. So if we look at a basic energy diagram, right? Let's say that we have something like this, right? Here on the y-axis we have energy, right? We have energy here, right? And let's say we have reactants and we have products. Okay. Now the way I've shown it, the reactants are at a higher energy than the products, right? So this reaction is exothermic. Right? What we can say is that initially when we talk about this reaction taking place, okay, we're breaking the bonds in the reactants. So that will be the bond energies of the reactants, and then we're forming bonds in the products, right? And for exothermic reactions, the bond energy of the products is greater than the bond energy of the reactants. In other words, we can say that more energy is released when bonds form in the products than the energy that was needed to break the bonds in the reactants. So we can say for exothermic reactions, okay, we can say the following. Okay, we can say that the bond energy of the products, okay, is greater than the bond energy of the reactants. Okay, more energy is released when bonds form in the products than the energy that was initially needed to break the bonds in the reactants, right? So therefore we get a delta H that has a negative value, right? Because bond formation is exothermic, bond breaking is endothermic. So here bond formation is greater in magnitude, so the bonds of the products are stronger. On the other hand, of course, if we had an endothermic reaction, right? If we had an endothermic reaction, then we would have the reactants at a lower potential energy, right? And the products would be at a higher potential energy, right? So again, what's happening here is that we're first breaking the bonds in the reactants. That's an endothermic process, right? That's an endothermic process, and then we are making the bonds in the product, right? So then initially we have bond breaking, and then we have bond formation. And for endothermic reactions, right, we can say that the energy needed to break the bonds in the reactants was greater than the energy released when bonds formed in the products. So we can say for endothermic reactions, okay, the bond energy of the reactants, is greater than the bond energy of the products. Okay. Here, of course, BE just stands for bond energy. And we can obviously look at the equation and identify that as well, right? If the bond energy of the reactants is greater, if this is a greater value, right, then the enthalpy change of the reaction will be positive, right? This will be bigger, this will be smaller, so we get a positive value. If the bond energy of the products is greater, right, then this value will be bigger than this value, and we'll get a negative value, which will be an exothermic reaction. So let's say I want to find the enthalpy change of the following reaction. Okay, I have the combustion of methane, CH4 plus O2 will give us carbon dioxide and water. Okay, in this case we're going to have steam. Okay, we're taking everything in the gaseous state. So let's say we have CH4 gas, right, oxygen gas, carbon dioxide is a gas, and in this case the temperature, we're carrying out this reaction at a higher temperature, so H2O is also a gas. We want to find the enthalpy change of this reaction, right? We have 2O2 and then 2H2O, right? We're given bond energy data, right? The CH bond has a bond energy of 410 kilojoules per mole, 410 kilojoules per mole. Okay. The oxygen-oxygen double bond, okay, the bond energy is 496 kilojoules per mole. The OH bond energy is 460 kilojoules per mole. And then the C double bond O bond energy for carbon dioxide, okay, is 805 kilojoules per mole. Okay. Now, of course, we can calculate this using the formula, right? The bond energy of reactants minus the bond energy of the products. However, what if we had to draw an energy cycle? Okay. Now, if you have to draw an energy cycle, if you're given data on bond energies, right, to complete that energy cycle, we're going to have gaseous atoms. Okay. Because, right, bond energy refers to when these covalent bonds are broken in the gaseous state and we end up making gaseous atoms. So over here, right, we can say that we're starting with the reactants, right? We're first going to break the bonds in the reactants. Okay, so here we have 1 mole of methane, right? We have 1 mole of CH4, right? 1 mole of CH4 has 4 moles of, we have 4 moles of CH bonds, right? This value that we have is for 1 mole of CH bonds being broken, so this will be 4 times 410. Then we have 2 moles of oxygen gas. Each molecule of oxygen has a double bond. If we have 2 moles of molecules, that is 2 moles of double bonds, right? So this will be 2 times 496. Okay. This will be 2 times 496. So now we've broken the bonds. We've broken the bonds in the reactants. We've broken the bond in the reactants, and now we're going to form the bonds in the products. Okay, we're going to form the bonds in the products. Okay. So here we have 1 mole of carbon dioxide. So we have 2 moles of carbon oxygen double bond, right? In every molecule of carbon dioxide we have 2 CO double bonds. We have 1 mole of this, we'll have 2 moles of the CO double bond, right? So this will be 2 times negative 805. Okay, the energy needed to break the bonds to go from the energy needed to break the bonds to go from the molecule to the atoms would be 805, right? When we're forming the bonds from the atoms, that's an exothermic process. Okay, so positive 805 is molecule to atoms, whereas from atoms to molecules it would be negative 805, right? Bond formation is exothermic, and we have 2 moles of H2O. Each molecule of water has 2 OH bonds. So if we have 2 moles of water, we're going to have 4 moles of OH bonds. Okay, we're going to have 4 moles of OH bonds, right? So we can say, okay, we can say over here that this is going to be 4 times negative 460. Okay, again, energy is being released when these bonds are being made. Okay, so negative 460 kilojoules per mole is the energy change when 1 mole of OH bonds is made. Okay, so it will be 4 times negative 460 because we have 4 moles. So we can say that the enthalpy change of the reaction, that's X, right? We can go directly from reactants to products. That will be the enthalpy change of the reaction, right? And that's the same as first breaking the bonds in the reactants and then making the bonds in the products. So we can say X is equal to 4 times 410 plus 2 times 496 plus 2 times negative 805, right, plus 4 times negative 460. So over here, okay, X will come out to, okay, over here X comes out to negative 818 kilojoules per mole. Okay, negative 818 kilojoules per mole. Okay, now obviously you can just say that the enthalpy change of a reaction, okay, you can just say that the enthalpy change of a reaction is simply the, okay, the enthalpy change of a reaction is the bond energy of the reactants, right, bond energy of the reactants minus the bond energy of the products, right? And this would be the bond energy of the reactants, right? You have 4 moles of CH bonds, so you have 4 times 410, 4 times 410 plus 2 times 496, right? And then you're going to subtract the bond energies of the products, right? So you have 2 moles of the CO double bond, so you're going to subtract 2 times 805, that's the bond energy of the CO bond, right? And then you have 4 moles of the OH single bond, so minus 4 times 460, right? So the answer will again come out to what? Negative 818 kilojoules per mole. Okay, so over here, okay, we can draw an energy cycle. Okay, if we're instructed to draw an energy cycle, in order to complete the energy cycle, we should have gaseous atoms. Okay, if bond energy data is given to us, right? And if you're not asked to draw an energy cycle, it's just easier to use the formula and calculate the enthalpy change of the reaction. Okay, you should get the same answer either way.